Right. Today we want to talk about phase portrait for linear systems with real eigenvalues. So this is the title I take from the book, but to be more careful, we really need to add with real. Actually, we need to add it here with distinct real eigenvalues. If we have repeated real eigenvalue, the phase portrait will look a little bit different than what we will be introducing today. So basically last time we talked about linear systems with two real eigenvalues. We know we are going to have exactly two straight line solutions. Okay, so the first thing we have is we will have straight line solution. Which looks like e to the lambda t times a vector. And here lambda is going to be the eigenvalue. And AB, the vector, is going to be the corresponding eigenvector. Okay, so what we will have is, whenever we have a system y prime equals ay, we just take this matrix out, we found lambda, we found v, and then we can actually have a straight line solution. And luckily, usually for a 2x2 system, we can have two pairs of eigenvalue and eigenvectors, which provide us two straight line solution. All right, so now let's focus on this straight line solution and what will happen to this. Well, basically this will be the phase plane with x and y. Now what you are telling me is you have a vector which is called AB, and then you multiply this AB with e to the lambda t. What does this e to the lambda t to do? Well, if you plug in different t, you are going to have a different constant here. And then you are using a different constant to multiply the same vector. What you're going to do is you are going to actually make this vector longer and even flip this vector if you times a negative number. This cannot do that, but if we have a general constant in the front, we can do this. But let's just go with the concept. And then basically for different t, we'll just make your point move on this line to different location. Okay, so this is t equals, I don't know, 1. Maybe this is t equals 2. And so on. Okay, so that's why we have a straight line solution. That's why this one looks like a straight line solution. Now, moreover, if I know the value of lambda, for example, if I know it's e to the 2t, what I will know is, as my t become bigger, this number become bigger, therefore the vector become longer. Okay, so if you think about it, what it will do is, it will take this vector AB, and as t goes by, it will make this vector larger and larger and larger. Therefore, t equals 1, t equals 2, t equals 3, t equals 4. I draw them to be equal to distance, but of course they don't have to be. Okay, so you can see there is a trend that if you let t become bigger, the whole solution is moving towards this way. Similarly, you can try it if you have a negative 2 in the front or negative number in the front. Okay, you will have some trend looking like this. From here we can see, well, easily by looking at this, we can tell this is going to be a source if you just care about this one dimension. So when lambda is bigger than 0, on this straight line, you are going to have this. Similarly, when lambda is less than 0, you can do the same analogy. When t become bigger, you have e to the negative 4t. When t become infinity, you will be ultimately very close to 0. Therefore, when t becomes bigger, this one actually goes back to the origin. Okay, it went from the very far away from infinity or initial value and come back to the 0, 0. So if we just care about what happens on a straight line, this will be the two cases. And the way to tell which case it is we look at the eigenvalue lambda. Okay, we wonder if it's positive or negative corresponding to e to the lambda t, which gives you something decreasing or increasing. All right, now when you put them together, you have two solutions, two straight line solutions. So how many different possible cases you can have? Well, the first case is going to be lambda is less than 0 on this, and lambda is also less than 0 on this. So we have both way, actually it's pointing towards 0, 0. You can have one direction is lambda less than 0, and the other one is lambda bigger than 0. Okay, so we have one way going in, one way going out. The last one is of course. Okay, the last one is going to be lambda bigger than 0 on this direction and lambda bigger than 0 on this straight line solution. So you have these three cases. Okay, that will be what happens on the two straight line solution. Now what we wonder is what will happen to the solution in this area, this area, this area, and this area. Now keep in mind, what do you have? What you have is your y is going to be any possible linear combination of these two solutions. Straight line solution. That means if you draw any solution here, you wonder what's going to happen. Well, in this direction, it's going to follow the trend here. In this direction, it's going to follow the trend here. That's what we call a linear combination of both. Therefore, roughly it's going to be like this. Similarly, roughly like this. In other words, if the two straight line solution actually points towards 0, 0, then any possible linear combination of these two will also point towards 0, 0. Similarly, we can do the same thing. If one direction is leaving, the other direction is also leaving, then if you put them together, any possible linear combination are also leaving. And finally, this is going into 0, 0, but this is going away from 0, 0. You will have some combination like this. Okay, so just knowing what's going to happen for these two straight lines, you will be able to know what's going to happen for any kind of solutions. Moreover, how do you know that what's going to happen for these two straight lines? You just look at two lambdas, right? So with all these things in mind, now we can actually write down this conclusion. Okay, we have three cases. The first case, we are going to have a sink. And how do you check that? You check both lambda are less than 0. Then you have a sink. For a source, which is something like this, everything is leaving. Therefore, lambda 1 bigger than 0, lambda 2 is also bigger than 0. Now finally, the one in the middle, we call it a saddle. That is going to be lambda 1 bigger than 0, and lambda 2 is less than 0, or the other way. You can also say when lambda times lambda 2 is less than 0, or you can say, when they have different sign. Either way, you know what I mean. Okay. Then you are going to have a source. If in every possible direction it's a source. You are going to have a sink if in every possible direction it's a sink. And you are going to have a settle point when in some direction you have a sink, and in some direction you have a source. That's the three cases. Okay. So it's very easy for us to try and see some examples. The first example is what I wrote here. And you can see you have two lambda. The first lambda is -4. The direction is 1, 1. The second lambda is -1. The direction is -2, 1. So you have two straight line solution, two distinct real value. On this straight line, it's going to be a sink. On this straight line, it's also going to be a sink because your eigenvalue is less than 0. Therefore, together, you are going to have a sink in all possible linear combination directions. And if we verify it, that's what we have. Okay, every blue line here, you can see on this blue line here, you are going to have in both directions, it's going towards 0, 0. Okay, now second case, very quickly. Positive, therefore it's a source in one direction, it's a source in another direction. Both directions it's a source, it's going to be a source in general. Okay, so you can see exactly the same straight line. as a streamline, but they're all leaving, simply because on this green and orange line they're leaving. Then all the possible linear combinations of these two vectors will be leaving. Okay. And finally, we can have the saddle. We can have two things. The first one is 1, 1. The second one is 11, 6. In the direction of 1, 1, we are going to have a sink. And in the direction of 11, 6, we are going to have a source. So in one direction, it's coming towards 0, 0. In the other direction, it's leaving 0, 0. So we're supposed to have a saddle. And you can see exactly. Okay. In one direction, which is the green direction, it's 11, 6. So everything is leaving. Meanwhile, in the orange direction, everything is coming in. Okay, so one direction is coming in, the other direction is leaving. Therefore, you have some kind of like coming in this direction but leaving in the other direction, so it turns away. That's basically what we have for this section. We just want a quick way to tell what's going on with the phase portrait. And we have three different kind of equilibriums: a sink, a source, and a saddle. So some side topics. The first one is, where does the name saddle come from? Okay. So basically, if you think about this, what we were drawing is, we were drawing this to be a source, okay, but in XY plane. And remember, every time we draw XY plane, we were always ignoring one more variable. That is, we still have a t. So technically, you can draw the whole thing into three-dimensional plane. Then what you're trying to see here, x and y, R is just a projection onto the bottom plane. Okay. So what do you really have for a source or a sink? This is what you have. So as time goes by, okay, basically you have something like this, where you have a local, I won't say local maximum, but it's more like in this direction and maybe in this direction. And in all possible directions, what you have is everything got, when t become bigger, which means when you go up, everything tend to actually go towards this one single point here. Okay, so that's when you have a sink. Okay, then what do you have if you have a source? You can imagine how to draw it. And you start from a point. As time goes by, you leave this point. So you can see these cases actually correspond to what we have for local maximum and local minimum in calculus 3. And that's exactly what's happening. Then you remember in calculus 3, if something doesn't have a local maximum or minimum, which means in some direction it's concaving up, in some direction it's concaving down, we of course have a saddle. So this is a source. And finally, x and y. In some direction it's going up, which means it's a source, like this. In some direction it's actually, let's draw this. Okay, it's actually going up, like this. So in this red direction, it's a sink because it's going towards 0, 0. Okay. In this black direction, you are going to be a source. So together, you are going to be a saddle, and it's not hard to see. Actually, this is the saddle point we typically see in 3-dimension in calculus 3. So that's where the name comes from. So it actually makes sense. It's not just an analogy. If you try to pump everything up for one more dimension into 3-dimension. Saddle point. So finally, how to interpret e to the lambda t? That's another very interesting question. So if you already have one direction, you have another direction, right? So basically, lambda tells you how fast when these two things go to 0, 0. For example, if lambda 1 equals lambda 2 equals negative 2, or let's say, not exactly this. Lambda 1 equals negative 2, and lambda 2 equals negative 3. That means for the same t, okay? If this is for lambda equals negative 3, they both go left and go down, okay? But the direction that you go to left is going to be faster because it has a bigger eigenvalue in terms of absolute value. So this one is going to decrease faster. Therefore, if it's 45 degree, same speed, it's roughly here, but this one is going to be leaning more towards like that. To indicate, okay, on this direction, it's actually faster. On this direction, it's actually slower. Okay, so that's actually how we determine all the straight lines. Like, if it's perfect, it's going to be 45 degree. Okay, but if it's not perfectly the same, you do have different speed. That's why when you actually draw it, you will have some extreme cases like this. Okay, in some direction, it's almost like horizontal. Not horizontal, parallel, because it's way faster than in the other direction. Okay. All right. Actually, you can see it from here. You have 1, 1 and negative 2, 1. 1, 1 is in the orange. Negative 2, 1 is going to be in the green. Okay. This 1, 1 have a negative 4 as eigenvalue. The green one has a negative 1. Therefore, negative 4 is bigger than negative 1 in terms of speed or absolute value. Therefore, all the straight line you draw will be more parallel to the orange line because you're faster in that direction and slower in the green direction. That's why you see all the lines looking like this. Okay, you can only be super fast in the green direction when you are very close to that direction. All right, that's all for today.